Hi everyone. So this is the recorded version for the exam to SI review. In today's review, we went over modules 4 through 5, but there was not module 6 on the review because I couldn't add it in time. But the updated review contains one or two questions relating to module 6, which has molecular shapes and dipole moments. Okay, so in this recorded session, I would go through all these questions one by one, just answer them to the point, and if you have any other questions regarding the question, feel free to email me to get more clarification on it. Otherwise, I'll just keep running through them. Okay. Question. Also, before I start this, I want to let you guys know that I highly recommend that before you see the answer to any of the questions, you try to answer them on your own. Best way would be to download the exam review and solve it on your own, and then see how your answers match with mine. It's a great way to recall things and memorize things. Otherwise, just watching it is of really no use. Okay, let me get my pen out. So question one is the distance between two consecutive peaks and troughs in a wave is called as what? And so in a wave, we have peaks and we have troughs. So the distance between consecutive peaks or consecutive troughs is called as the wavelength. Since it's a length, it's measured in either meters or most probably in nanometers. Okay. What is one packet of light energy called? And so if you remember, light is quantized and energy is quantized in general. And so when it's released, it releases as packets. And when it comes to light, it's called as photons. Okay. Formula for energy of a wave, I'm sorry. Formula for energy of a wave of light is called as what? And so this is a straightforward formula. I would say memorize it. It's E equals hc over lambda, where E is the energy you're trying to find. H is the Planck's constant, and c is the speed of light, and lambda is the wavelength. Yeah. Question 4. What is the approximate visible spectrum of light? And so in this question, I'm trying to ask you from what wavelength to what wavelength can you see light? And the approximate wavelength would spectrum would be 400 to 800 nanometers. Yeah. Anything before this falls under the ultraviolet spectrum. Anything after this falls under the infrared spectrum. Cool. Question 5. Find the energy of light of wavelength. What? I'm sorry. Find the energy of light of wavelength 400 nanometers. So you have a wave. You have a wave of light with lambda equals 400 nanometers, and the question is to find the energy in it. And so I've given you the values for H and C, and all you have to do is plug it in and find it. I would recommend trying to do the math on your own. It's a little complicated. Um, Once you're done doing it, then come see how I solve it. So to solve this, what I'll do is I'll say E equals hc over lambda. I'll plug the numbers in, 6.626 times 10 to the power. In this question, I personally am not caring much about significant figures because I want you to learn how to solve the question instead of actually caring about other things. This is terrible. I'm not doing very well right now in this review. Okay. I only care about how you do the math. You can figure out significant figures on your own. So plug in the numbers in. H is this times speed of light is 3 times 10 to the power 8 meters per second over lambda is 400 nanometers. If you see seconds here, cancel off. We want the answer to be in joules because energy is written in joules. However, we have meters and nanometers, we don't really cancel off because they're not the same unit. So I would say either convert your meters to nanometers or convert nanometers to meters. The conversion factor is 1 nanometer is 10 to the power negative 9 meters, or you can say 1 meter is 10 to the power positive 9 nanometers. Any one is fine, they're both correct. I'm going to plug this over here. So this would become, I'll erase this off, and then it'll be times 10 to the power negative 9 meters. And then to do this math, what I do first is in my calculator, I will only plug in the non-power numbers. So what I mean by that is I'll do 6.626 times 3 um, divided by 400, and that gives me 0.0496 and something ahead of that. And then I'm going to use the exponents in my, like I'm going to do by hand. To solve the exponents, you take the numerator, I have negative 34, and it's been multiplied with positive 8. So I'll add 8 to the exponent, and it's been the whole thing has been divided by negative 9. So to bring it on top, I'll reverse the sign and write 9. And then I can solve this in my calculator. Negative 34 plus 8 plus 9 gives you 0.0496 times 10 to the power negative 17. This is a right answer. You convert this. I want my answer to be in something like 4 point something. So I'm going to say I need two decimal places. I'm going to do 100. I'm going to multiply and divide by 100. I'm going to apply this multiplied number to my actual number, my magnitude. That'll make it 4.96. And then I'll apply my division to this number. Since I'm dividing by two zeros, I'm going to subtract two zeros from here. And that'll make it negative 19. I apologize. And then my answer was in joules. So I'll write joules over here. Yeah. You might know the formula, how to plug it in, but if you mess up with the math, your answer will be wrong. So I highly recommend you practice doing a little math revolving around this. So even if you know the method, you don't get the wrong answer. That'd be pretty stupid and waste of time. Okay, if you figure that out, why don't you try doing this one? Find the energy of light of wavelength 800 nanometers. So it'll be the same method with different numbers. And if you do the math, your answer should be 2.46 48 times 10 to the power negative 19 joules. Okay, awesome. I'm gonna save this so my PC doesn't crash. Okay. Next question is find the wavelength of light of energy that many joules. So now I'm giving you a value in joules, and I want you to find the wavelength of the light. And so to do this, try by yourself first, and then once you're done trying, come back to the video. I'm gonna keep solving it. We use the same formula, E equals hc over lambda. I'm gonna rearrange this to get in the form of lambda equals hc over E. To do this, all you do is multiply both sides by lambda and divide both sides by E. So the E cancels off here and what's left is lambda. And the lambda cancels off here, what's left is E. And then in this form, all you do is plug numbers in. H is 6.626 times 10 to the power negative 34 joules second times speed of light is 3 10 to the power 8 meters per second. And energy is given in 4.42 times 10 to the power negative 19 joules. My joules cancel off, seconds cancel off. What's left is meters. I can do this math on my calculator. 6.626 times 3 divided by 4.42 gives me, I'm going to round up to 4.5 times 10 to the power. Let's see, I have negative 34. I'm multiplying it by 8, so I'm going to add 8 to it. Divided by negative 19, so I'm going to change the sign and write 19 as it is. That should be negative 34 plus 8 plus 19. And that would give me negative 7. You can leave the answer in here as meters, but if you want to convert it to nanometers, remember the conversion factor for this was, I'm going to write it over here. 1 meter is 10 to the power 9 nanometers, or the converse would be 1 nanometer is 10 to the power negative 9 meters. I'm going to multiply. I don't want meters, I want nanometers. And I say 1 meter is 10 to the power 9 nanometers. And that would give me 4.5, oops, meters cancel. What's that nanometers? 4.5 times 10 to the power negative 7 plus 9 is 2, which is 450 nanometers. Okay, that's how you do the math for this one. Awesome. Okay, if you have any questions regarding anything, feel free to email me and I'll try to answer it over email. Moving on, the question 8 is smaller the wavelength of light, blank the energy. So I want you to relate how is energy related to the wavelength. You can go back to the previous questions, question 5 and 6, where I gave you 400 nanometers and found an energy of 4 point something, and 800 nanometers found the energy of 2 point something. And so if you see, as you had more wavelength, your energy decreased from the previous question. Another way to think of this is you can use the formula. Um, so you say E equals hc over lambda, and the relation between this formula is lambda is in the denominator, while your answer E comes in the numerator. And so as you increase lambda, the fraction would net decrease. So there's an inverse relationship. As lambda goes higher, E goes smaller. And so the inverse of that would be as lambda goes smaller, E will become bigger, right? Like example, 1 over 10 is smaller than 1 over 100. Apologies, this is incorrect. 1 over 10 is bigger than 1 over 100, right? So bigger your fraction is, bigger the denominator is, smaller the fraction becomes. So the relation between lambda and E is inverse. So smaller the wavelength would mean a higher energy. So the right answer is higher. Okay, moving on to the next one. A quick reminder that when you excite an electron, you expect it to go to a higher energy state. That's true. But after you stop exciting it, you expect it to come down to the ground state. And so when the electron comes from the excited to the ground state, the difference in the energy would be released as light. And you would expect that if the electron lives anywhere in the atom, if the possible states can be anything, the electron can jump to any height from the nucleus. And when it comes back down to the nucleus, it would release energy as light of any wavelength possible, right? But the reality is it does not release any wavelength. It releases only discrete wavelengths, like specific numbers of wavelengths. And that suggests that the energy levels in an atom are not like any possible spectrums, but the discrete levels around the nucleus where the electron can live in. And those and that like led to the theory that energy in an atom is quantized and not in the spectrum. And so then my question with this note is, what are these fixed positions in the atom around the nucleus called? And the right answer to this is shells. And so electrons live in shells of fixed energies, and each shell has its own capacity. Is question 12. But question 11 is, what is the name of the quantum number associated with shells? And the symbol for that is n, as someone mentioned in the SI review. But the name I was looking for is principal quantum number. Principal quantum number is what shells are also known as, and they're denoted by n. So n can take the value of whole numbers starting from 1. So n can be equal to 1, n can be equal to 2, 3, 4, and so on. Okay. Again, coming to the capacity, every shell has a capacity, the highest number of electrons it can hold. And so the question is, how do you calculate the capacity? And to calculate the capacity, there's a formula. The formula is 2 times n squared. Remember, the square applies to, oops, this square applies only to n and not to the 2. So the formula is 2 times n squared. And then take an example for this. What is the capacity for n equals 2? So I will take n as 2, square it. That gives me 4. And then I'm going to multiply this 4 by 2 because of this 2. And then I get 8. The capacity of the shell n equals 2 is 8. Okay. A reverse question could be, if I tell you the capacity and ask you for the shell number, So this question says, which shell can hold at the most 18 electrons? So I'm telling you, 2 times n squared equates to 18. Can you find n? So to do this, you divide the whole thing by 2, which would cancel off this 2, give you 9. So what's left is n squared equals 9. So you'll say n equals square root of 9, which would be 3. The capacity of shell n equals 3 is 18. Okay. You can do the same thing for n equals 1 and n equals 4 as well. Question 15 says, write the shell electron configurations of lithium and sodium. And what I mean by this is of the kind 2, 8, 2, 8, 18, 32, I'm sorry, and so on. And so to find this, the simple way is you say lithium, it's Z equals 3, the atomic number. So it has 3 electrons. I'm going to put those 3 electrons in shells as I go from shell 1, shell 2, shell 3. Shell 1, the capacity is 2. So out of these 3 electrons, I can only put 2 electrons in the first shell. I now have 1 electron left. I'll move to the next shell. The next shell's capacity is 8. I only have 1 electron left, so I'm going to put it in there, and that will be a configuration for lithium. In case of sodium, I have Z equals 11. Now, I have 11 electrons to fill in. The first shell can only hold 2 electrons, so I'm going to put 2 in there, and then I have 9 left. The next shell can only hold 8. I have 9 left. I'm going to put 8 of them. That leaves me with 1 electron. The next shell can only hold 18 electrons, and I have 1 left, so I'm going to put 1 in there. Okay, and that's my configuration for sodium. If I have to do one more as an example for you guys, I'd say magnesium 12. First shell can hold 2. I'm going to put 2. Out of the 12, I've placed 2 over here. I have 10 remaining. The next shell can hold 8. Out of the 10 remaining, I'll put 8 over here. Leaves me with 2 electrons. The next shell can hold 18. I only have 2 left, so I'm going to put those 2 in there and then call it good. Okay, perfect. If you have any questions about this, feel free to email me. I'll help you with that. Question 16 is, number of electrons in the outermost shells are called as what? And so in the outermost shell, which is this one, the number of electrons will be called as the valence electrons. Okay. Okay. So the electrons in the valence shell are the valence electrons, or the outermost shell are the valence electrons. Question 17. Elements in the same blank have similar electronic configurations and hence have the same number of blank electrons. And so the answer I'm looking for in the first blank is either groups or periods of the periodic table. If you remember, the elements in the same group, in the same vertical line, have similar configuration. As you can see from here, lithium and sodium are in the same group, the first group, and they have similar configuration where it's something, 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 comma 1, something, 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 comma 1. So the first blank is groups, and they have same number of blank electrons. So if you observe in this case, they both have the same number of valence electrons. Okay. So with that, if you think about magnesium, below magnesium is number 20 calcium, and so calcium would have a similar electronic configuration of something, 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 comma 2. So if you try filling out the configuration for calcium 20, you'll have 2, 8, 18, 2. Okay. Next one. Refer to the diagram below which transitions will release most energy and which transition will have, I'm sorry, will release most energy and which transition will release energy with greater wavelength. And so you have transitions going from n equals 2 to n equals 1, and this arrow shows that. And another transition is n equals 3 to n equals 2, which this arrow shows. The question is, which transition, let's call this transition 1 and let's call this transition number 2. So between 1 and 2, which one would have greater energy and which one would have It says greater wavelength. And a good way to think about that is look at the arrow. This is a bigger arrow showing that there's a greater energy difference between these two shells. And so the energy released would be greater in transition number two. And we said energy and wavelength are inversely proportional. And so greater the energy, smaller your wavelength, right? Because it's reversed. So because transition 2 has a greater energy compared to transition 1, the wavelength of transition 2 would be smaller. And so wavelength transition 1 would have a greater wavelength of the energy released. Okay. Next question is, if the unit conversions for electron volts to joules is given by this conversion factor, convert 100 joules to electron volts. And this is a straightforward conversion. In essence, it's similar as converting from meters to nanometers. And so to convert this, I'll write 100 joules. Um, I do not want joules. I want electron volts. And so it says, oops, it says 1 eV equals to 1.602 times 10 to the power negative 19 joules. And so all you have to do is plug this in to your calculator. 100 divided by 1.602, which gives you 62.42, and then negative 19 in the bottom comes up to become positive 19 joules. I'm sorry, not joules, electron volts. So these joules cancel off. Okay, that's your answer. It's a straightforward conversion, just has a very ugly factor to convert with. Okay, question 20. To make chemistry a bigger pain in the bottom, there exist subshells within shells. Can you name the 4 types of subshells? Um, if you remember, the 4 types of subshells are S, P, D, and F, and they reside within the shells. So shell 1 only has subshell S. Shell 2 can have subshell S and P, because it's a little bigger than subshell 1, bigger than shell 1. Shell number 3 can have subshells S, P, and D, and shell number 4 can have subshells S, P, D, and F. Okay. Question is, what is the capacity for each subshell? And good way to remember it is you write S, P, D, and F, and you start with 2 because one's capacity is only 2. And then you add 4 to consecutive ones. So 2 plus 4 is 6, 6 plus 4 is 10, and 10 plus 4 is 14. Okay, that's the capacity for each subshell. Okay, moving on to the next one. Can you write the electronic configurations including subshells for neon, magnesium, argon, and bromine? Um, so this one is a little annoying because you have to follow this off of principle. I think I turned my pen off. Okay, so how this works is I'll show you with neon. Neon is 10, and so you start with this point and you go towards the arrows. The first thing you encounter is 1s, so it'll be 1s. Capacity of s is 2, so I'll write 1s2 on the top, a notion of writing how many electrons there are. Out of the 10, I have placed 2 of them. I have to place 8 more. So I keep following the arrow. The arrow ends. You jump to the next arrow and you see 2s. 2s can hold 2 electrons because s can hold 2 electrons. So I'll place 2s2. Out of the 8 remaining, I placed 2. I have 6 more to go. I keep following the arrow and then I reach 2p. I have 6 left. Capacity of p is 6, so I'll put 6 over there, and that's it. That's my configuration for neon. It'll be 1s2, 2s2 to p6. Okay. I'm going to zoom through all these other, but the method remains the same. All you do is you follow the arrows and you keep jumping to the next arrows and you keep placing electrons. Magnesium is 12. If I follow the arrows, my answer comes out to be 1s2, 2s2, 2p6, and 3s2. Argon is 18. Argon is 1s2, 2s2, 2p6, 3s2, 3p6. And lastly, bromine. This is going to be a bigger one. Bromine is 35. Bromine's configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3, 3d10, and 4p5. Okay, let's count. These are 10 electrons. These give you 10 electrons, so the 10 plus 10 gives you 20 electrons. 10 more gives you 30 and 35. Okay, I placed all electrons in the right order. That's your configuration. Um, can you abbreviate the configurations of magnesium and bromine using noble gases? And so what I mean is, if you look at neon's configuration, it fits exactly inside magnesium's configuration for this part, right? So you can abbreviate magnesium 12 as core electrons of neon plus 3s2. That's the abbreviation. For bromine, you can see argon's abbreviation configuration fits perfectly until here. So you can replace that, and then you can write bromine 35 can be written as mm, argon 4s2, 3d10, and I'm sorry, 4p5. Okay. And so to write abbreviated configuration is very convenient because it shortens the configuration by much. I saw bromine had a big configuration. Now it's just 4 things in there. But the problem is if you want to write both of them together and then combine it, it just wastes time and defeats the purpose. So there's a shortcut way of writing abbreviated configurations if you have your table on hand. And so I'm going to use the example of astatine and iron. Astatine 33 is right over here. And so to solve this, what you do is you backtrack it, you go to the left and you find the first previous noble gas. In this case, it's argon. Argon's 18. So you would write astatine 33 equals core of argon, and then you go towards right. Before we go to the right, let me give a few notations. These first two groups are in a clump of 2, and it coincides with the S subshell having capacity of 2. This bunch of groups actually involve helium as well. These bunch of groups falls have 6, like are a clump of 6 groups, which also coincides with the shell capacity, subshell capacity of P equals 6. And this bunch of groups are, there are 10 of these, and this coincides with the D subshell having capacity of 10. Okay, so starting from argon, you go left, you say this is 1, 2, 3. This is the 4th period in the periodic table. So you say 4s1, 4s2, and the S ends over there. So I write argon 4s2. I keep moving. Comes the D1. For D, I will reduce this number 4 by 1 and write 3. There is 3d1, 3d2, 3, 4, 5, 6, 7, 8, 9, 10. So I have 3d10. I keep moving. I enter the P subshell. I'll go back to the 4 and write as it is. 4. I'm over here. 4p1, 4p2, 4p3 is where astatine is. So I'm going to write 4p3, and that's my answer. Okay. Let's try this once more with iron. Iron Fe is 26. It is right over here. If I backtrack it, oh, again, argon is the first previous noble gas. So I will say core electrons of argon. I'll go towards right again. I start with period 4, 4s1, 4s2. I enter the D subshell. I have D becomes 4 minus 1, 3. I will write 3, 3D1, 3D2, 3, 4, 5, 6 is where iron is. So 3D, 6. And then you have to go any further because that's where iron ends. So that's my configuration for iron. Okay, sweet. 25. Oh, before I go ahead, um, can you guys name how many valence electrons are there by using the configurations given to you here? Okay, so so the good way to do it is just count whatever left is here. But there are a few rules associated with this. Valence electrons can be calculated as electrons in the outermost shell or in the incomplete shells. Okay, if you're using the configurations. So the outermost shell would be the highest number of n equals something. In this case, the highest number is 3, and there are 2 in there. So the valence electrons for magnesium are 2. In bromine, the highest number is 4, and 4 has 2 plus 5. So my total, I have 7 valence electrons. I am also mentioning D over here, but D is completely filled, so I don't count that for valence electrons. Okay. In case of acetine, again I have highest number as 4. It has 2 plus 3, so total I have 5 valence electrons in acetine. D is not incomplete, it is completely filled, so I won't count that for valence electrons. However, in iron, the highest number I have is 4, but I also have an incomplete D shell. It's not 10, it's 6. So I'll have 2 plus 6, I'll have 8 valence. Okay, perfect. Moving on to the next one. If you have questions regarding this, please email me and I'll walk you through it again. Okay, the next question says, as you go left to right in a period, the atomic size blanks. And so what happens to the atomic size as you go left to right in a period? So a period is the horizontal lines, and as you go left to right, you keep adding new electrons to the same shell. Like if I go back to a question where I had written the configuration for, okay, I don't have it yet, I'm gonna rewrite it. You had sodium 11 and magnesium 12. Sodium was 1s2, 2s2, 2p6, 3s1, while magnesium was 1s2, 2s2, 2p6, 3s2, 3p6, and 4s1. Wait, I apologize. That is incorrect. That is not true. I don't know why I went so ahead. Okay, this is magnesium. 10 plus 2 is 12. And this is sodium. As you can see in this case, your outermost shell is the same, 3s, but you have one extra electron in magnesium going into the 3s shell. And so that puts an extra electron in the outermost shell and one new proton in the nucleus, making the attraction between the shell and the nucleus stronger, and the shell shrinks in size to come closer to the nucleus. It's like magnets. When you have two strong magnets, they come like closer because the attraction force between them is stronger. And so as you go left right in the period, you add new electrons to the same shell, and that decreases the atomic size. So the atomic size decreases, gets smaller. Next question, as you go left right in the period, what happens to the ionization energy? And so a reminder what this means. Ionization energy is the energy required to remove one electron from the outermost shell of a ground state atom to make an ion. Okay, so I'm trying to remove an electron from the atom. And as you go left to right in a group, let's say, I'm sorry, in a period, let's say you start with lithium, period number 2, and you want to go to neon. Neon is a noble gas, and noble gases have the most stable configuration. So anyone who is close to neon would not want to go further away from neon, would want to look more like neon. So as you go left to right, it gets very hard to remove electrons from that atom to make it have a smaller electron number. And as you go left to right in a period, it gets harder. That means you need more energy to remove the electron, and hence the ionization energy um, oops, increases as you go left to right in a period. Another way to think this is because the atomic size decreases so much and the electrons are so close to the proton, it's much harder to remove them apart because their attraction is stronger. Okay, as you go top to bottom in a group, what happens to the atomic size? Um, a good example for that would be, let's say, lithium and sodium. Lithium is 3, sodium is 11. Lithium is 1s2, 2s2, 2p. Oops, no, that's too many electrons again. 2s1, and sodium is 1s2, 2s2, 2p6, 3s1. And so as you can see, differences, lithium has the maximum shell number 2 and sodium has maximum shell number 3. There's one extra shell in sodium. That means it goes up by a size. And so as you go top to bottom in a group, atomic size increases. Okay, increases. Perfect. And as you go top to bottom in a group, what happens to the ionizing energy? As you go top to bottom, we said the size increases, so the outermost electron goes further away. That decreases the force between the attraction force between the electron and the proton, and it becomes much easier to pull out the electron in the same group, and so it'll decrease because it's much easier to pull out the electron. You need less energy. So as you go top to bottom, the requirement decreases. Okay. What is the general outermost electronic configuration for noble gases? And if you go back to the one where we had neon and argon mentioned, if you see neon ends with 2s2, 2p6, while argon ends with 3s2, 3p6, and so you can predict that krypton, the next one, would have something, 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 4s2, 4p6. And so the general trend you see in these guys would be the configuration is something, 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 ns2, np6. Okay, so every atom wants to look like this because this is the most stable configuration. What does the octet rule mean? The octet rule means that every atom wants to have 8 electrons in its outermost shell. Where the 8 number comes from this. 2 plus 6 gives you 8. That's what the octet rule means. Octet rule means that every atom wants to have 8 electrons in the outermost shell. 31 says, by the octet rule, metals tend to blank electrons and non-metals tend to blank electrons. And so the blanks have either option gain or lose. How do you find that? Let's take, for example, lithium. Lithium is 3. I have 1s2. Actually, let's take sodium. It's a better example. 11 would be 1s2, 2s2, 2p6, 3s1. And let's take fluorine, which is 9, 1s2, 2s2, 2p5. And the closest noble gas between these two guys is neon, and neon's configuration is 1s2, 2s2, 2p6. Yep. Um, and so what can sodium and fluorine do to look more like neon? And one thing they can do is, in case of sodium, this is the configuration of neon, this is excess. So if it loses this one electron out, it look like neon. And so sodium is a metal, and every metal would have a few excess electrons compared to the closest noble gas, and they will want to give out the electron to look more like the noble gas. And so by the octet rule, metals would tend to lose electrons, and then that will make them a cation, which are positive charged ions. And then if you look at this non-metal fluorine, fluorine has 9 electrons, which is one less from neon. So if I add the one electron over here, it'll become 2p6 and start looking like neon, right? And so every non-metal will always have a few electrons lesser than the closest noble gas, and they will want to gain electrons to look like the nearest noble gas. And by gaining, they'll become an anion, which are negative charged ions. Okay, moving on to the next question. The next question says ionic compounds are formed between blank and blank only. And to form an ionic compound, you need to have an ionic bond. An ionic bond is a bond in which electrons are completely transferred, not shared, completely transferred. And this complete transfer happens only when you form ions, right? And metals from cations and non-metals from anions. So the answer to this question would be metals and non-metals only. You cannot have two metals forming two cations coming together because they'll repel each other. You cannot have two non-metals forming two anions coming close together because they'll repel each other. Metalloids do not form ions complete anyway. So the only option remains is taking a metal and a non-metal. They have opposite charges and they'll attract. Okay. Following that, question 33 asks, ionic compounds don't have molecules per se because they form long-range, highly ordered structures called as blank. And the follow-up to that is the opposite of this is called as blank. And so if we take the example of, in this case, NaF, we write them as NaF because the ratio is 1 to 1. But in reality, there are so many Na ions and so many fluorine ions that they form a long, very ordered structure called as a lattice. And to be accurate, it's not any kind of lattice, it is a crystalline lattice. Okay? A crystalline lattice is very highly ordered and the order extends to a long range. And the opposite of a crystalline lattice is amorphous. Amorphous lattice. Okay. Crystalline lattices are usually formed of salts and crystals. Amorphous are like of other things, like for example, chalk is amorphous. Okay. I would also recommend going to your lecture slides and memorizing the properties of crystalline lattices. Okay, there are 3 or 4 properties. Just memorize them. It's probably good for exam. Okay, next question is which of the following are ionic compounds? And a good way to differentiate between ionic compounds is seeing if the ions involved in it are of metals and non-metals. And the first one is sodium chloride. Na is a metal, sodium is a non-metal, and NaCl is an ionic compound. Nitric oxide, N is a non-metal. If you look in the periodic table, N is a non-metal, O is a non-metal. Two non-metals form covalent bonds, not ionic bonds. That's not an ionic compound. Silicon is a non-metal, oxygen is a non-metal. Two non-metals do not form ionic compounds. Mg is a metal, Cl is a non-metal. We have 2 of them, but that's fine because we have a metal non-metal forming an ionic compound. Lithium is a metal, fluorine is non-metal. They will form ions and hence that's ionic. Carbon is a non-metal, oxygen is a non-metal, cannot form ionic compounds. Okay, awesome. Question 35. It asks, what is the Coulomb's law formula? And so the formula for Coulomb's law is force of attraction between two charges is given by K times Q1 times Q2, the charges of charge 1, charge 2, over the distance r squared. Okay. These are the charges between which the force is attracting or repelling, and this is the distance between those two charges. Not r squared, just r. You square the number. Okay. And so what are the interpretations of Coulomb's law? What I mean is by changing the charge and distance, how would the force change? And you can see the two charges are in the numerator. That means if I increase my charge 1 or if I increase my charge 2, that would mean I increase my force. Okay, because they're directly proportional. However, um, the distance is the denominator, and so they'll have inverse proportionality. That means if I increase my distance, I will actually decrease the force of attraction between them. Okay, and the reverse is true. If I decrease the charges, I'll decrease the force. If I decrease the distance, I'll increase the force. Okay. Question 37. How can you describe the cut or break made to a crystalline lattice? This is one of the properties of crystalline lattices, that when you cut or break a crystalline lattice, you have a perfect cleavage plane. Okay, it's because they're so highly ordered um, structures with the ions. When you break them, they break perfectly apart into now two long-range, highly ordered crystalline lattices, where the break is a perfect, like straight, clean-cut plane. Okay. If I need X amount of energy required to break the lattice of a compound, assuming it's crystalline, I should say break the uh, crystalline lattice of a compound. What is this energy called? Actually, that this can be said even for any kind of lattice. So I'm just going to say if I need energy to break a lattice, any lattice is fine. What is the energy called? Another way to say this is if a lattice is held together by a certain amount of energy in it, and if I overcome that energy, the lattice will break or like give apart, not just like cut into pieces, like completely fall apart. What is the energy called? And this energy is called as the lattice energy. Okay. Question 39. How is a covalent bond different from an ionic bond? And so the answer for this is the covalent bond is formed by complete sharing of electrons. I shouldn't say complete, it's just a sharing. A covalent bond is formed by sharing of electrons, whereas an ionic bond is formed by complete transfer of electrons. Okay. Question 40. Draw the Lewis dot structures of all these elements. And so all these elements are period number 2 and period number 1 elements. And these are very commonly used for drawing Lewis dot structures. So to draw them, you write the element's name and you write how many valence electrons you have as in dots. So hydrogen only has one electron in the valence shell, so I'll draw one dot next to it. This dot can be anywhere, can be top, bottom, left, right, doesn't matter. Just draw the right number of dots and it should be fine. Lithium has 3 electrons. However, it only has one electron in the outermost shell. And so I would draw lithium as lithium dot. Yep. Beryllium has 2 electrons in the valence shell, so I'm going to draw beryllium as 2 dots. Could be anywhere again. Boron has 5 electrons, 3 in the outermost shell. I'm going to draw 3 dots for boron. Carbon will have 4 dots. Oxygen would have, nitrogen would have 5 dots, and the fifth dot gets paired up to make a lone pair. Oxygen has 6 valence electrons, so I'm going to draw 4, and the last 2 get paired up. And fluorine has 7, so I'm going to draw 4, 5, 6, and 7 get paired up. Okay. Okay. So that's how you draw the Lewis dot structures of these compounds. Question 41. Um, it's a reminder note, not a question. It says steps for drawing Lewis dot structures of molecules. So these are the steps you'll use to draw molecules. Let's like start with an example so you can go back and see how to do it. Draw the Lewis dot structure for CH4, NH3, O2, and like all of these. I'm going to quickly open a paint window so I can draw side by side. So the first one is CH4. To start drawing CH4, what I'll do is step 1, calculate total number of valence electrons. And so carbon has 4 valence electrons, while hydrogen, each hydrogen has 1 electron. We have 4 of them, so I'll write 4 electrons, and there'll be 8 electrons. And so next step says connect all the atoms to a central atom with single bonds. So because there are 4 hydrogen and 1 carbon, I'm going to assume that carbon is a central atom, I'm going to connect these 4 hydrogens to carbon using single bonds like this, and then count how many more valence electrons are left to be assigned. I should add a quick note there saying if there are any remaining, add them as lone pairs. Okay, and so every bond has 2 electrons inside it, and so I have 4 bonds. 4 times 2 is 8. I have used all my electrons, and so I have none left, and so that's my configuration. Oh, the last step says check to see if any octates are completed or not completed. If the octates are not complete, make multiple bonds to complete them. Mm, I wasn't sharing my screen. I'm sorry for that. Okay, Zoom doesn't show me if I'm sharing my screen or no. I hope I'm sharing my screen. I hope you can see this. If not, I'll just re-record the video. But okay, that was how to draw CH4. Now, next one says NH3. I'm gonna go backwards because these are more difficult ones. So I'm gonna start from here. Um, to draw NH4 plus, you count how many valence electrons there are. N provides 5 electrons. Hydrogen, this one provides 1 electron. The 5s have 5 valence electrons, and the charge +1 means I have lost an electron from the molecule. So I'm going to reduce 1. I'm sorry, N has 4. This should be 4. Again, N has 5. There are 4 H's, is what I meant to say. So 4, 9, 5 plus 4 is 9, minus 1 is 8. NH4 plus has 8 electrons in it, valence electrons in it. I'm going to draw single bonds connecting to a central atom. That's step 2. Step 3 is count how many more valence electrons are left to be assigned. Oops, forgot the 4th one. And then assign them as lone pairs. I have 4 single bonds. Every bond is 2 electrons. 4 times 2 is 8. So I have used all 8 of them. And so there's none to be assigned. And that's my final structure. I can go ahead and put a bracket and say it's plus sign because it's NH4 plus. But that's my final structure for the compound. Okay, let's try drawing one more. Next one is NO3 minus. And so I'll say NO and the 3 O's. N gives you 5 valence electrons. Oxygen gives you 6 times 3. So really it gives you 18 valence electrons in this compound. And there's one negative sign, which means there's one extra electron in the structure. And so 18, 19, 19 plus 5 is 24. I have to assign 24 electrons to the structure. I'm going to start by connecting nitrogen to 3 oxygens by single bonds. 3 bonds means 6 electrons. So I've consumed 6 electrons over here. Leaves me with 18 more electrons to be assigned. I'm just going to start assigning 18 electrons as lone pairs. Starting from the outermost, coming to the innermost. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I'm going to assign 3 lone pairs to each because 3 lone pairs plus 1 bond gives you an octet. So it completes the octet of the oxygen. So I move to the next one after that. And so I've assigned all my 18 electrons. I have none left to assign. Now I have to check for octets. If you see, this oxygen has 3 lone pairs, 1 bond. That means 8 electrons. So this has a complete octet. This has a complete octet, and this has a complete octet. However, nitrogen only has 3 bonds, 6 electrons, so it needs 2 more. I could make this oxygen share a lone pair to make a new bond, and so that would look like this lone pair goes away and becomes a bond over here. And now this still has an octet. There's 2 bonds and 2 lone pairs. 4 times 2 is 8, but nitrogen now has 4 bonds and hence has an octet. So that also has a complete octet. And I can go ahead and say this has a net negative charge because there was a negative charge on it, and that's your final structure. You can have this double bond either here or over here or over here, and it's valid in all cases. It's just resonance structures NO3 minus. They're all correct structures. Okay, next one is BeCl2. And I brought up this question on purpose because Be is an exception to the octet rule. I'll show you how. Be only has two valence electrons in the outermost shell, while chlorine has 7, and there are two of them, so they really have 14 contributions, and there is no charge. So I total have of 16 valence electrons in this molecule. I'm going to start connecting to a central atom by 2 bonds, single bonds. I have used 2 bonds, that's 4 electrons, leaves me with 12 lone pairs to be added. I'm going to start adding 12 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I've used all 12, I have 0 left. Let's see octates. Chlorine has a complete octate, this chlorine has a complete octate. Beryllium is an exception, it only needs 4 electrons in the outer motion, it does not need an octate. So they all are satisfied among themselves, and that's my final structure. Okay, I'm going to delete these so I can draw some more. Next one I need to draw is, oops, I need to draw BF3. I brought this up because B is another exception. B can only have 6 outermost electrons in the outermost shell. I'm sorry, 6 valence electrons in the outermost shell. So let's say boron has 3 valence electrons. Fluorine has 7 times 2, 7 times 3, which is 21. That gives me 24 electrons to fill in. I'm going to start drawing single bonds to fluorine. I have used 3 bonds, 6 electrons. That gives me 14. Wait now. 1, 6, 7, 8, 9, 10, 11, 12, 13, 14. 18 more to fill. And so I put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18 lone pairs. 18 electrons as lone pairs. I have 0 left to fill. Checking for octates. Fluorines have octates, so they're all satisfied. Boron is an exception. Boron only needs to have 6 total electrons in the outermost shell. Right now it has 3 bonds, 6 electrons complete. So boron satisfied as well. And that's your final answer. Okay. I think I made a mistake earlier. What I meant to say is beryllium needs a total of 4 electrons in the outermost shell, not an octate, 4, and boron needs 6. I don't remember what I said earlier, so I'm going to correct myself right now. These are exceptions to the octate rule. Another exception is hydrogen, which only needs 2 electrons in the outermost shell. Okay, sweet. That's complete. We can draw some more structures. The next structure is CO2, carbon dioxide. Carbon has 4 valence electrons, oxygen has 6, and there are 2 of them. So really there are 12 valence electrons by oxygen. If I add them, I get 4 plus 12 is 16. To draw, I want to start drawing single bonds to connect the central atom to every element, and then I have used 4 electrons in 2 bonds, leaving me with 12 electrons to still add as lone pairs. I want to start from here: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I've added all 12. No more left to add. I'm going to check for octates. Oxygen and this oxygen want octates, and they have 8 electrons, so they're all full. Carbon only has 4 electrons, so I'm going to make this oxygen share electrons. I can also make this one share an electron, and that will make it have this structure, and then there'll be still 2 lone pairs left over here. Yeah, that's my final structure for carbon dioxide. I think you would also make this oxygen share 2 and this oxygen share none, and that would be a resonance structure of carbon dioxide. That's correct too. Okay, next one is SO2. And SO2 is a little complicated. Sulfur and oxygen are in the same group, so they have same valence electrons. Sulfur has 6, oxygen has 6, but there are two of them, so really they have 12 in this molecule, and you have 6 plus 12 is 18. I will draw sulfur in the middle and connect oxygens to it. I've used 4 electrons in this, and that leaves me with 14 to add as lone pairs. I'm going to start with oxygen 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then 13, 14 go on sulfur. And so I've used all these 14 and I've left 0. Check for octates. I bring this question up again because sulfur is another exception. Sulfur can hold 8 um, or can go all the way up to 12 electrons in the outermost shell. It would like to have at least 8, but it has a capacity to hold 12 in reality. Okay, so oxygen has complete octet. This oxygen has a complete octet. Sulfur only has 1, 2, 3, 4, 5, 6. Um, for the sake of symmetry in the atom, both these oxygen provide it with lone pairs as shared, and the structure looks like this for sulfur: 1, 2, 3, 4, 1, 2, 3, 4, and then 1, 2. As if you see, this oxygen has 8 electrons, and the octet's complete. Sulfur now has 1, 2, 3, 4, 5, 6, 7, 8, 9. Right now it has 10 electrons, and that's fine because it has the capacity to hold up to 12 electrons. And so that's the correct answer. You could leave it here. It could be a resonance structure, or you could make multiple, like triple bond here, single bond here. That's also a resonance structure. Or just single bond here, no bonds here. That's also a resonance structure. That's fine. Okay. If that's clear, we can move on to the next one. Next one's O2. O gives 6. The other O gives 6. So you really have 2 electrons to fill in. There's no central atom, so I want to connect them together. I have used 2. That is, one bond has 2 electrons. So I have 10 more to fill in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Check for octates. This oxygen has an octate, but this does not have an octate. So what I'm going to do is I'm going to make this share electrons, and then I get a double bond, oxygen, oxygen. There's 2 lone pairs left over here, and this one only had 2 lone pairs to start with. And that is the structure for oxygen. Okay, last one is NH3. N gives you 5 electrons, and hydrogen gives you 1 electron. There are 3 of them, so I'm going to put times 3, so 3 electrons. Total, I have 8 valence electrons in this entire molecule. I'm going to start by connecting single lines, single bonds to the hydrogen with the nitrogen. I have 3 bonds, so I've used 6 electrons and I have 2 left. I'm going to place these 2. Now, hydrogen can only hold 2 electrons in the outermost shell. It has a bond that is 2 electrons, so it's completely packed. All these 3 hydrogens are satisfied. This nitrogen only has 6, so I can put 2 more here to make its octate. And I've used these 2 electrons. And so what's left is check for octates. We said hydrogen was satisfied. This nitrogen has 3 bonds, 1 lone pair, that's 8 electrons, so it's satisfied. No need for multiple bonds. This is the final structure. Okay, and we already do CH4, so we have drawn all these molecules in this video. Awesome. Okay, moving on to the next topic is what is electronegativity. And so I can say electronegativity is the tendency of an element to pull electrons, or you can say attract electrons towards itself. Okay, and so this comes in play mostly when you have covalent bonds, because in a covalent bond, for example, I have to draw, let's say I am drawing carbon monoxide. It has 3 bonds in it, um, and one lone pair here and one lone pair here. And so oxygen is more electronegative than carbon, and so the electrons would go more towards oxygen. There's a way to denote it. I should modify the question, say, give an example and draw the polarity of the bond. And so the polarity of this bond would be, since oxygen is more electronegative, uh, you can find the electronegativity of oxygen and carbon and subtract them, and you'll see the electronegative difference would be greater than 0. And if it's greater than 0, the electrons will move towards the more electronegative atom, in this case oxygen. And so to draw that, you draw an arrow pointing towards the direction where the electrons move towards oxygen, and you make like a plus sign to the side where there's like a net positive charge, and that's the polarity of the bond. Okay. Question 44. If there is a difference in the electronegativity of two bonded nonmetals, the bond is said to be what? And so that's the previous example. I have two nonmetals, and there is a difference in the electronegativity, and so this bond now has unequal sharing of electrons, and that bond is called as a polar bond or a polar covalent bond. Okay, cool. Next question. Name the following compounds. Um, so this comes into nomenclature. Uh, the first compound is Al2O3, and Al is a metal, oxygen is a non-metal. This is an ionic compound. And the name format for these compounds is, you write metal blank ide, and so this one would be aluminum oxide. I think I misspelled aluminum. Okay, aluminum oxide. Next one is Na3N. Na is a metal, N is a non-metal. Again, a metal blankite. This will be nitrogen nitride. Next one is also a metal non-metal ionic compound. This would be lithium chloride. Okay, until now you had all these metals fall under either the first two groups or the last 6 groups. No one fell under the middle 10 groups of the transition metals. And the problem with transition metals is that they can have multiple charges on them. So you have to calculate what charge your transition metal holds in this compound and then name it. So cobalt chloride 3. Each chlorine has -1 charge, and you have 3 of them. So net total charge of 3 chlorines is -3. And so this one cobalt atom is nullifying the -3 charge. So it must hold a +3 charge. Okay. And hence the name of this compound would be cobalt. You mention the +3 charge as Roman numerals in brackets after cobalt, and then you say the good old chloride. Chloride. Okay, perfect. Now again, Sn is tin. Tin is also in the transition elements. So I'm going to quickly calculate the charge on tin. SnCl4. 1 chlorine is -1. 4 chlorines is -4. 1 Sn satisfies 4 chlorines. That should be +4. And so my name would be tin 4 chloride. Okay. So that was all metals and non-metals. In this one, if you see, it is a non-metal and a non-metal. And the name format changes here. The name format would be number, name, number, blank, id. Okay. What I mean is, you mention the number for the first one, you write the name of the first element, you mention the number for the second element, you write the name for the second element as an id. And so you use the numbers from this table. 2 means di, first is sulfur, And then second number is 10 for fluorine, so 10 means deca, and then it's fluoride. Disulfur decafluoride is the name. Okay, next one. Um, OS is osmium. Osmium is also another nonmetal. Now, osmium is only one, so you don't really have to mention mono for it. You can just write osmium. 4 means tetra oxide. Another rule is if your name, I typo, if the number of the second name has a vowel in the end, like here I have an A, and if your name of the second element has a vowel to start with, like here I have oxide has an O, you can completely skip the last vowel of the number name. So it can be osmium tetroxide, and that's correct. Okay. Same would be if I, like, for example, if I had osmium pentoxide, it really is penta, but because you have the A and the O, you write pentoxide only, and that's fine too. Okay, the next one is more than one element. So you won't say trisodium phosphor trioxide. That's not correct. This, the PO4 is a polyatomic ion, and so refer to this chart to get the answer for that. This is a metal and a bunch of non-metals. So this also follows the metal blank-eyed name. Uh, but the blank-eyed is really from this table. So the first metal here is sodium, and then PO4, if you see over here, is phosphate. So it's this sodium phosphate. Okay, you can do this for any metal and polyatomic name from this chart. The next one is HCl. Now HCl are two non-metals, but because it's H, it's an acid, and there's no oxygen involved, so it's a simple acid. And the name for simple acid is hydrohaloide or hydrohaloic acid should be more appropriate. Halo means what halogen you're using. So for this one, it would be hydrochloric acid. Okay. Same can be for HBr, hydrobromic acid. HI would be hydroiodic acid. Okay. HF would be hydrofluoric acid. This is an oxy acid because contains an H acid, also contains O, so oxy acids. And if you see, NO2 is a group present in this chart over here, is a nitrite group. A little new rule, if you have an ite for an acid, it becomes us. If you have an ate for an acid, it becomes ik. So nitrite, it, would really become nitrous, and so I would name this as nitrous acid. I don't have to mention the hydro for this because it's an acid is given. Okay. Another example would be ClO. ClO falls under hypochlorite. It become us, so it'll be hypochlorous acid. Yeah. I want to give more examples for this one. Let's say H3 ClO4. Now ClO4 is the chart as perchlorate. Chlorate, it becomes it, so it'll be perchloric acid. Okay, great. Someone in the session asked me a question about the multiple charge transition metals. How do you find the charge? And the question they asked was, can there be a metal with very, like in this case, like cobalt COL4? It was obvious that this 4 is the charge for cobalt, but is there a case where that's not true? And that is a case. My favorite one is FeO, oops, FeO and Fe2O3. One thing to remember, oxygen always has a negative 2 charge, and so hence iron should be a positive 1 charge, a positive 2 charge. Yeah, that was pretty easy. But there was only one here, but the charge wasn't 1 because the charge on oxygen is -2 really. Okay, so this one would be iron 2 oxide. The next one, every oxygen is minus 2 charge. There's 3 oxygens, so all these total give you a minus 6 charge. Okay. You have 2 iron atoms or ions, so both of these together should have a plus 6 charge, but it's 2 of them, so I'm going to divide it by 2. So each one of them really has a plus 3 charge. So this compound is really iron 3 oxide. Okay, iron brackets 3 oxide. Awesome. I want to save it. The next question is, I don't know why this got shifted. Find the steric number of the central atom for the following molecules. Once you know the steric number, use it to find the electron group arrangement and molecular shape of the molecule. While you're at it, draw the polarity of the bond and determine if the molecule has a net dipole moment. Okay, let's start finding by the steric numbers. And to find steric numbers, you draw the molecule, and then you calculate in the central atom how many bonds you have and how many lone pairs you have. Okay, I'm gonna go back to the paint over here. We drew CH4 earlier. Oops. Earlier as C, 4 bonds with H, and so carbon here has 4 bonds and no lone pairs, so my SN number is just 4. Okay, so here SN is 4. I should write SN equals 4. BeCl2, I drew it as Be, and then I drew 2 bonds for Cl, and then chlorine has a bunch of lone pairs. We don't care about them. We only care about the central atom. It only has 2 bonds, no lone pairs. Hence, the steric number for BeCl2 is 2. Okay. We never drew HCN. I can draw HCN for you. If you follow the rules, HCN would look like this. Okay. We don't care about the outermost elements. We only care about the central one. The central element has 4 bonds, no lone pairs. That means, I'm sorry, there are SN equals 4. Okay. It's important that you draw C in the middle because there's another compound, H and C, and that has a different steric number. Actually, it has the same steric number as 4, but it's a different compound, so don't worry about it. NH3, I'm going to miss some space. NH3, we drew NH3 as N, 3 bonds with H, and 1 lone pair. Now there is 3 bonds plus 1 lone pair gives me 4. So NH3, SN is 4. For BF3, we drew BF3 as B, 3 bonds F. Remember, boron is an exception to the octet rule. It can only hold 6 at the most outermost electrons. And so boron has 0 lone pairs plus 3 bonds, giving you SN equals 3. SO2, we drew SO2 as the structure. So sulfur now it has 2 double bonds, but we only count every double bond as one bonding group. And so it should be 0 plus 2. I'm sorry, my bad. It should be 1 lone pair plus 2 bonds. I should say 2 bonding groups. That gives me SN of 6. Okay. So a triple bond, I didn't mention earlier, I'm so sorry for this. HCN, you may be confused. Carbon has this one bonding group and this one bonding group. So it's a triple bond, but really it only has two bonding groups. So this 4 is incorrect. It should be 2. CN has a SN of 2. This triple bond counts as a one bonding group. I'm sorry for that. Sorry for the mistake. SO2 has SN of 3 because there's 2 bonding groups of 2 double bonds and 1 lone pair. So SO2 is 3. Okay. H2O. We never do H2O, but you can practice drawing it on your own. H2O looks like this. It has the oxygen has two lone pairs and two bonding groups, so really it has four steric number, SN is 4. Okay, and now to talk about electron arrangements and molecular shapes, I'll go back to full screen. Um, electron arrangements are given in this table, and so this is the SN number over here, 2, 3, 4, 5, and 6. No matter how many bonding groups or lone pairs you have in the given SN, the electron pair geometry remains the same. You only have different molecular shapes. Okay, so first one, we have CH4 SN of 4. Now SN4 lies in this row. It depending on how many lone pairs you have, your molecular shape will change. And so CH4 only has 0 lone pairs, all 4 are bonding groups. So CH4 falls under this group, tetrahedral. So CH4 would have electron arrangement of tetrahedral and molecular shape also of tetrahedral. Okay, BeCl2 has SN2, so it falls under this one. There's no other possibility, so only thing it can be is linear. So BeCl2 has electron arrangement of linear and molecular shape also linear. Okay, HCN. HCN has SN2. Again, it falls only under linear, so there's electron arrangement and molecular shape. They are all linear. Okay, NH3 has SN of 4. It falls under this column, so it'll have an electron arrangement of tetrahedral. But because the one lone pair is there, it's called tetrahedral, but the one lone pair has nothing attached to it, but it still contributes. Okay, let me reframe it. The one lone pair is still there, so the 3 bonds in the one lone pair have a arrangement of tetrahedral, but because nothing attached to it, it does not contribute to the molecular shape. You don't see it. You don't see the bond. So the molecular shape looks pyramidal. I should say trigonal pyramidal. Trigonal pyramidal. Okay, just pyramidal is fine too. BF3. BF3 has SN of 3. It falls under here. So its electronic arrangement given over here would be trigonal planar, and its molecular shape would be BF3 has no lone pairs, so it's not bent. It is trigonal planar. So its electron arrangement and molecular shape is the same. SO2 is SN3, so the same column, same row, but SO3 has one lone pair and two bonding groups, so it really looks like this structure. So its electron arrangement would be trigonal planar, but its molecular shape would really be bent. Okay, why is this incorrectly? Okay, I don't know what's happening with Word. Anyway, H2O. H2O has SN of 4, so it falls under this category. So its electron arrangement would be tetrahedral, and its molecular shape would be H2O has 2 bonds and 2 lone pairs, so it falls under the 2 lone pair group, so it'll be bent also. Okay. While we are at it, why don't we talk about molecular bond angles? And so bond angles is for linear because it's a straight, it'll be 180. Trigonal planars are 120s, and bent, they would be less than 120. Why less? Because This lone pair now comes closer to the central atom, pushing the other bonds a little closer. Okay. For tetrahedral, it's 109, and then this would be less than 109, and this would be much, much less than 109. I think your lecture slides say this one is 107 and this one is 105 degrees. They're all in degrees. Okay. We never had an example about this. I would say example for trigonal bipyramidal would be PCl5. It looks like this. You'll have P and you draw 5 bonds with Cl on it. Okay. Now you say, oh, phosphate doesn't have an octet. It has a like 10 electrons in outermost shell. Because phosphate is also an exception to the rule. Phosphate can hold 8 electrons, but can really go all the way to 10. And sulfur, like we said, can hold 8, can go all the way to 12. Okay. You know what? I want to summarize all the exceptions. You have these over here. You have boron, which can only hold 6. Beryllium can only hold 4 electrons in the outermost shell, and hydrogen can only hold 2. So you have these 5 exceptions to the octave rule. I think you should remember them. Okay. In trigonal bipyramidal, you have 2 bond angles, one of 90 and one of 120. Okay. Octahedral is when you have SN of 6. Example for this would be SCl6. Sulfur can hold like 6 bonds. And so here you only have one kind of bond angle, 90 for all of them. Okay. Cool. Oh, there's one part left. It said, while you added, draw the polarity of the bond and determine if the molecule had net dipole moment. So going back to the paint window. Oh no, I have to draw everything again. So CH4 has delta En. Give me 1 second. I'm gonna pull up the chart for delta En square around memorized. Okay, so I've pulled up the chart for electronegativity. It's in the lecture slides, so you can refer to that. Carbon has a negativity of 2.5, hydrogen is 2.1. So 2.5 minus 2.1, 2.2 minus gives you 0.4. So it is greater than 0, right? So there'll be a dipole moment um, towards the more electronegative atom, which is carbon. So I'm going to draw it like this, like this, like this, and like this. But if you see, they're all pointing towards the same. So this guy and this guy cancels off. This and this cancel off. So you have a polar molecule. You have polar bonds between C and H, but your net molecule is not polar. There is no dipole moment. So question is, are there polar bonds in CH4? Yes, there are. But is there a net dipole moment? No. Okay, so I can mention this over here somewhere. CH4, oops, polar bonds with no dipole moment. Okay, BeCl2 looks like this, right? Now beryllium has En of 2, while chlorine has En of 3. So this one is more or less negative. So there'll be a net movement towards both the chlorines, but because they're symmetric, they cancel off. And so again, I'll have the same thing where my bonds are polar, but there's no net dipole moment. Okay, in case of HCN, hydrogen has 2.1 electronegativity, carbon is 2.5, and nitrogen is 3. So from the central atom, um, nitrogen is more electronegative, so move over here. but between these two guys, carbon is more electronegative, so it'll move towards here. Now these both point to the same direction, so they'll add up, and so I will have a net dipole moment towards nitrogen. Okay, so for HCN, I should say it's a polar bond with dipole moment, and I can say nitrogen. Um, I should say towards nitrogen. Okay, awesome. Um, oops, I didn't mean to do that. Delete. And then next one is NH3. We said NH3 has a peculiar shape of pyramidal, and so they all point towards one side like this. N has a negativity of 3.0 and hydrogen is 2.1, so they'll move towards the nitrogen, and so these would cancel off with each other, but this one would stay, and so there's a net dipole moment towards nitrogen. Okay, so it's also important how you draw the molecule, draw the most truest molecular shape, so they really they act like what happens in reality. So I would say there is polar bonds with dipole moment again towards nitrogen. While I'm inserting new lines, my drawing got completely destroyed. Okay. We said that. BF3 BF3 is trigonal planar. Oops. It's trigonal planar. Boron has negativity of 2, while fluorine has 4.0, and so it'll move towards the fluorine atoms. Again, these guys would cancel off because symmetric, but this would remain, and so my net dipole moment is towards fluorine. And so in case of BF3, I'll have polar bonds with dipole moment as a towards fluorine. Okay. SO2 look like this, and S has a little negativity of 2.5. Oxygen has a little negativity of 3.5. So oxygen is more little negative, so it'll move towards oxygen. And the bond is polar, but since they're symmetrically opposite, going to the same direction, they won't cancel off. They'll add up towards here. Okay, so they're not really canceling out, they're adding up towards one side. So SO2 would be with dipole moment pointing between oxygens. Okay. And so in the previous case too, like NH3, these guys don't really cancel off, they add up over here. So I should correct myself. This is incorrect. I should write NH3 like this. And so these guys will move here, these guys will move here, this will move here, and so these guys would add up to give here a net dipole moment, and then these two would add up to give a bigger dipole moment towards nitrogen. So it still is towards nitrogen. I just like said incorrectly when I added it. In this case too, boron F3. We said it moves towards fluorine. So these two would really add up to give you towards here. And then this is a weaker one. Actually, I'm confused now. Hold on to this one. BF3, I'm not sure what the answer is. So do not follow this one. This could be incorrect. I'll ask Dr. Peters and get back to you about this one. So leave BF3, but everything else should be correct. And that's the end. Oh, we forgot H2O. So H2O was drawn like this. Um, nope, that's incorrect. I'm tired. I'm sorry. Um, H2O is drawn like this. H has a negativity of 2.1, and oxygen has a negativity of 3.5, and so it moves towards the oxygen. And so the net electronegativity would add up and would look like this towards the oxygen. And so H2O has uh, okay. H2O has polar bonds with dipole moment towards oxygen. Okay, and that's the end of the review. I will post this solved review on the SI website as well under resources, the same place where you found this video. But if you have any other questions about the exam, feel free to ask me, email me, and I'll help you with it. My email ID is dakghone@iastate.edu, or you can contact me through, contact your SI leader option from the SI webpage, and I can help you from there as well. For the exam, I'll just say all the best, do well, keep calm, and I think you can use your open lecture notes, right? So refer to lecture notes for things like the chart about the nomenclature and molecular shape, so you don't get confused. Otherwise, all the best for exam, and this is it for the exam review. Thank you for watching this long video. How do I stop sharing? Goodbye.